All right, I'm gonna go through some of the basics that should have been covered last week in probably this video and maybe one more. Probably split it up. But we're basically just looking at equations of motions for planar rigid body motion, which is not that different than the particle motion that we've already looked at, but there are some extra terms to deal with rotations. So in the general sense, same as with kinematics, we're looking at objects that are moving in a plane, so they can have essentially two translations and one rotation, and the rotation is always about plane. That's the general sense. So in what's drawn on screen here, your rotations would always be about the z direction. That's close enough. And in terms of the actual equations of motions, what that adds is a summation of moments. So as opposed to the summation of forces, you've now got a summation of moments. And whereas a summation of forces is equal to mass times acceleration, here we've got the mass moment of inertia, which we did talk about on Monday, multiplied by an angular acceleration. So if I were to add, well, first off, we still got the sort of, if we're just looking at a rectilinear system, we still have forces, equations of motion in x and y, which look the same as prior. We do want to note that these are about the center of gravity as well. So these would be accelerations that, if I sort of draw in a kinetic diagram, your accelerations are going to be at the CG of the object, which is denoted with G here. So I'd have AX and AY like so. And then the summation of moments would also be in that location. So I'm going to draw it positive by the right-hand rule, and that means that my alpha term is also going to be about G. So that's what we end up with in terms of the general equation of motion. And then when we look at a just general translation, the first thing that we'll see is for a rectilinear system, which is more or less just your Cartesian x and y. All that happens with that is in my three equations of motion, x, y, and z, your moment term is always going to sum to 0. And that would be that term there. So you can still have applied moments to the object if we've got some object with a center of gravity and there's a moment over here, call that M1, there's another moment over here. Those have to sum to 0, so basically M1 would have to be equal to M2 and well, minus M2, I guess, the way I've got them drawn. They would have to cancel out, basically. So you can still have moments applied to a system and end up with rectilinear translation, but the moments are always going to cancel out. So in terms of the equation of motion, you still got that term. That can still be useful for solving problems out because it can give you information about your moments. And as you know from statics, your moments and forces can have some relationships as well. And when we get to an example, we'll go through that in some detail. Then in terms of translations, the only other thing that we're really going to look at here is we can still have curvilinear motion, which we've looked at in terms of mostly normal tangential and polar. In this case, we're only going to cover normal tangential, and there's nothing really different here. We've just got everything written in terms of normal and tangential components. That'd be a T. And still the summation of moments is of course going to be equal to 0. So this would be you're just following a path, and you're same as before, your normal tracks normal acceleration tracks a change in velocity, normal acceleration tracks a change in direction. That's very similar definitions to what we've used already. Now, when we start to pick up some newer information is when we do factor in rotations. And this is just like kinetics or kinematics of a rigid body. We're going to look at translations, which is just really that. This is no different than particle kinetics really, because you're not dealing with any actual rotations. But we just want to keep in mind that extra equation, summation of moments has to be equal to 0. That does help solve these problems. That's the big difference between translation particle kinetics and translation of rigid body kinetics, is you do have that summation of moments equal to 0. But then when we talk about the planar rotations, basically, this would be pure rotations with no translation. So we dealt with only translations, now we'll deal with only rotations, and of course we'll combine the two together. And for this one, if we just look at some object that is pinned in space, in this case, so we've just got kind of a rotating joint there at O, and it's got some center of gravity out in space. And then we'll say that there is an applied alpha term and an applied omega as well. So this has some rotational acceleration velocity. And then this is just a general case, so I'm just going to throw some random forces on it as well. Something like that. In a couple of moments. And then what we're going to have in terms of accelerations for this will essentially be, of course, the whole thing has got, I guess I should do alpha and omega for my rotational accelerations. Those can be converted into translations of the CG, because this whole thing is rotating about point O. So if I sort of think of a radial line that goes between O and G, as that's rotating, everything, you've got a fixed point of rotation, so everything is going to rotate about that point. So you'll actually have just a circular path of rotation as this thing rotates, and that would be true for any point on the object. It's moving in a circle about point O. Let me get rid of that. And as such, that basically means that G is following a path. If an object follows a path, it's often convenient to think of that as a tangential acceleration. So at G, at this instant, we can break the translation of G, or the accelerations of G, into a tangential and a normal component. So AGN, just like that. We still have alpha and omega up here, or alpha, I guess in this case, that's causing these accelerations, and alpha and omega together are causing those accelerations, but that's sort of the addition of them, or they create the linear translations as well. Things only rotating, but any point on the object is going to have normal and tangential acceleration because it's rotating about a fixed point. So looking at it in those terms, we're going to write out equations of motion as summation of forces. These summation of forces are still at the CG. So we'll have the mass times the acceleration at G in the normal direction, and summation of forces in the tangential direction, like so. And then summation of moments about G. Now the summation of moments is going to be equal to mass moment of inertia at G times alpha. And then our two terms here, those can be written in terms of alpha and omega as well. So normal acceleration will have the mass. The normal acceleration is omega squared rg. And then our tangential acceleration is going to be just alpha times rg. And that's it. So if you've got something rotating and you know alpha and omega, you can figure out the linear components of acceleration, and those can go into the equations of motion for pure rotation, just like that. So that lets you solve a pretty good variety of problems. Now you're not always all right. So this specifically was about summing moments and forces about a CG, but it's worth noting that you don't necessarily have to sum moments about a particular point. And this is another thing that you might recall from statics, is that you take a summation of moments about any point, and the moments are gonna work out essentially the same. There are limits to that statement, but they generally work okay for simple statics problems and simple dynamics problems. But in this case, what I'm getting at is, say we wanted to sum the moments about point O instead of the center of gravity G. Well, we'd still get summation of moments about O. In this case, all we got to do is use the mass moment of inertia at O instead of G. So using the correct moment of inertia pretty much takes care of any issues that might, it takes care of the geometry shift. You can write out inertial moments in certain ways, and people do that. That is explained often in textbooks. But essentially, if you're writing out an equation of motion, anywhere you choose to sum moments is fine. You just need to be able to calculate the mass moment of inertia at that point. Which if you know it at the CG, then you can calculate it anywhere else with the parallel axis theorem, which is quite nice. All right, now we're looking at general plane motion, which isn't going to be any major difference than what we've looked at. It's just at this point you've got to consider, you're not considering the point to be fixed. There's no fixed point of rotation, rather. So this thing, it's general shape. This is this can rotate at any time in space, and it can translate as well. So this is free to move and rotate as it pleases. So it could be just translating, it could be just rotating, but equations of motion will track whichever the case may be. So for this, you do have to have some sort of reference system, of course. And I'm just going to throw it in an X and Y, which is perfectly fine for this. And then we're still going to track our accelerations at the CG. So those will be AG terms. And then skip that. And then the moment, we're still going to sum moments about G. They're going to be equal to IG times alpha. And there's really no additional expansion or simplification of that that's particularly needed. That relatively well covers it. Once we get into solving some problems, you'll see how some of the planar kinetics comes into play to be able to solve complex or more complex problems than a simple translating rotating part. But we'll get to that in the examples here shortly.